In this presentation, we're going to look at trusses, specifically the finite element formulation to solve trusses. And to do this lecture, you need to prepare a little bit. If you want to follow along completely, go to the lecture materials. The link again is below. And go to the notes folder, download Trusses FE formulation if you want to follow along with the notes, or at least have those for you to refer back to later. Also go into the Mathcad folder and download the Trusses example. It's empty because it's basically I haven't put anything into it yet, which we're going to do as we work through the example, so then you can save a kind of a full solution of the example that we're doing. All right, so you can go grab those files and come back and we'll be ready to go. All right, so we're looking at trusses. So here's an example of a truss. And these structures are typically classified as trusses or frames, also called frames. And what we're looking at when we say something is a truss or a frame, they have the following characteristics. They're all two-force members. There's no bending. So two forces just right along the axial piece of our members. They're pin joints, which are good assumptions, even with bolts or welds. And you can see here we have a pin joint up here on the left, and we have a roller joint here on the right. And loads are applied at the joints, such as we have here with the 1,000 pounds and the 2,000 pounds. So statically determinate trusses are assumed to be rigid bodies and solved using method of joints and sections. This is something you learn in statics, so relatively something we can do by hand calc relatively easily. When we look at statically indeterminate trusses, they must be solved by allowing them to displace. We need some deformable bodies and use geometric constraints or boundary conditions. It's a long, tedious process. But what the advantages with finite element method is we can solve both statically determined and indeterminate in a very straightforward manner. So that's what we're going to show you here today. So the finite element formulation, this is looking at the direct stiffness method. So we have a two-force member here. We've got a force being applied in either direction. And it's going from an initial length, L, to a final length, delta L. And we can look at that. We can find out the stress from the force over the area and the strain from the displaced length over the original length. And so from Hooke's law, we relate the stress to the strain using the modulus. And if we substitute in for the stress and the strain, we get this formulation of F over A equals the modulus times the change in length over the initial length. Solving for the force, we get AE over L, and that's, as we looked in the previous lecture, analogous to our spring, a linear spring. So F is equal to K times A. All right, so our K equivalent for a two-force axial loaded member is AE over L. And now we could substitute basically just our K now in for our AE over L for our stiffness of our member. So to continue this formulation, we need two frames of reference because we're doing stuff within the member, but then we also have to relate the member to the overall truss or frame that exists. So we're going to have a global coordinate system, which is how we look at the overall structure of all the members. And we'll have the local coordinate system to just one member, to just one piece of our whole system. So let's look at how we're going to have those, because this is a pretty key relationship between these two as we move forward. So looking at the coordinate system, the global coordinate system will be used to define the node locations, where they are in all the space, element angles, constraints or boundary conditions, external loads, as well as the overall solution displacements that we're going to come up with. And we'll talk through all, and you're going to see all these as we go through the presentation here. The local coordinate system will be used to define individual element behavior and values. So within individual element, we're interested in internal forces, displacements of the element itself, and element stresses. So let's go look at that. Here we go. All right, so here's the overall global system. So you can see global X and Y, kind of how we usually represent it. Y is vertical, X is horizontal. And we'll have some displacements of our nodes globally. So capital U is used for the global displacement. And of this node, say the J node, one side of our member, and it has both an X and Y component. Same thing at the I node on the other end. If we look at the local system, now we're going to look locally to our element. We're going to have the X component be along the axis of our member, and the Y component is in the other direction. So we have the displacement in the X direction at both the J node as well as the I node. And we have this overall angle. Now note this angle. This is pretty key. We're going to measure this angle from horizontal. So we see from horizontal, we go from the global x component, and we go up from there to our local x component. So that's pretty key when we do that jump. So when we look at the example, you'll see that we're going to always go from a horizontal angle, start at horizontal and move up to where the axis of our member is located. So there's a summary of all the notation that'll be on the handout if you want to check out there, but you'll catch a lot of it as we go through. All right. So then we have these trig relationships. How does the local coordinates relate to the global coordinates? And so we have this. So if we looked at just the cosine of I sub x, so if we look at the cosine here, which should be this distance right here, all right, you can see that's how that's part of the global displacement in the x direction, but we are going to also subtract off the sine of the direction here. So if we look at the sine of UIY, right, we're going to have this distance here. So obviously not drawn to scale. All right. So again, this is theta here. So when we look at this theta, so the sine would be this distance right here. Right? But it would propagate down here. So not to scale as probably as much as it should be, but overall you get the sense of where these two values are coming from. So we can do this also for the other global coordinates, creating those from the local coordinates. And this is going to be a pretty key thing as we look in the next couple slides here. All right. Forces, we can do the same thing. So we have global coordinate system, and we have our global forces at each node, again broken into components of x and y. And we can look at the local version of those, again some theta angle up from horizontal to the local forces being felt by the member. And they have the same trig relationships relating the local forces to the global forces. All right, so we have these displacements, the global displacements at either node, so node I and node J of our member. And from those, we also have some local displacements, as well as global and local forces. So all of those, again, kind of the notation as we discussed are there. All right, so just kind of summarize, we can put those into our matrix format. So going back to that trig relationship we talked about, we have the local displacements, and if we have the trig relationship that gets them over to the global coordinates. So how do we get from the local to the global? We have to do cosine theta of the local displacement at node I in the x direction minus the local displacement at node I in the y direction, sine theta there, and we get the global displacement in the in the x direction at node I. Now you can see here, hopefully, that we got kind of a system of equations. We can get that, put that into matrix form. All right, so we have our global coordinates for our element, and we have the local coordinates for our element, and we have this new t. All right, this t is going to be called our transformation matrix. All right, so looking at the next page here, again, it's just going to involve this cosine and sines that we have here. So they're the same cosines and sines, and you can track back to the previous slide and see how you have the different local versus global coordinates going on there. But this is the transformation matrix, because what it does is it transforms our local coordinates into our global coordinates. It does it with the displacements as well as with the forces. So the transformation matrix transforms local values into global values. This is going to be very key for what we're doing here, kind of moving between the different coordinate systems. All right, so if we look at our truss element, look at both the forces and displacements. The forces we can get from the change in displacement multiplied times the stiffness of our element. Right? And because we're looking at trusses, there are only two force members along the axis. So we're only interested in the displacements in the x direction, the local x direction. Right? So the forces that we're going to have at node I in the x direction is going to be k times the change in displacement along our member, and as well as the forces at node J in the x direction are going to be the displacements in the along the member, only in the x direction. So we're not looking at any forces in the y direction in the local coordinate system. We're local to the member, just this one particular member. All right, so if we put that in matrix form, right, so we'll have, just looking at this, the force, and then we have the stiffness. So here's the stiffness, positive stiffness. And then we have, and then negative is going to be, as you multiply and distribute this K3, you're going to get a negative value there. And we have the same thing for our force at node J in the x direction. So we get the minus K there and the positive K. Right? So again, these K's going back, we said for a member, and looking at our statics analysis with stress and strain, is it's AE over L for our equivalent stiffness for a member. All right, so notice the matrix equation form. We got these local forces equals the stiffness matrix times our local displacements. We're going to convert these over to global coordinates because we need to, again, this is one element and we need to attach it to all the other elements making up the whole system, the whole truss frame system. All right, so we know the global force. We can get to the global force and we can get to the global displacement if we multiply the local displacement and the local force by our transformation matrix. All right, so we know that. And so if we take the inverse of our transformation matrix, we multiply both sides by the inverse of the transformation matrix, we end up with this on the left-hand side. And the inverse times the inverse transformation matrix times the transformation matrix gives you the identity matrix. So basically there's just a 1 right here after you do the multiplication, and there's a 1 right here. All right, so that's why you don't see anything on the right-hand side there. All right, so if we substitute into this equation or substitute what we just saw for here, right? So we just saw for these two equations. If we substitute this back into this equation up top here, right? So F becomes the inverse of the transformation matrix times the global force equals, substituting in for the local U, we got the inverse of the transformation matrix times our global displacements. Right? Now we multiply both sides by the transformation matrix. So we multiply these two together, that's going to give us the identity matrix, and they're going to go away. And again, we're multiplying by the leftmost side to make sure we're consistent on our matrix math. So then we get the transformation there, and so we end up with how we can get the global coordinate form based from our element stiffness matrix. All right, so you'll see what it is on the next slide. But again, we've seen all this stuff before, so what's different? Let's watch what happens here. By the way, so here's the inverse transformation matrix, just so you know. In this case, it's just the transform of the transformation matrix. So a lot of transformation, transforms, a lot of similar terms there, but just make sure you understand which is which. All right, so just noting here what the inverse transformation matrix is. All right, so we're going to substitute the transformation matrix, the local stiffness matrix, the inverse of the transformation matrix, all into our equation we just came up with, and it simplifies to this. All right, so we got all our global forces over here. Again, this is just I and J, so this is just for one member. All right, and then over here we have our global displacements at the nodes on either side of our member. And now what we have here in the middle is our global stiffness matrix for one element. Right? It's not the global stiffness matrix for the whole system, it's just for one element. Right? So it relates the applied forces and the stiffnesses and the displacements for one element, all in the global coordinate system. All right? The K we had before was a lowercase k up here, because this K was not in the global stiffness matrix form, it was in the local stiffness form. So the global stiffness form, we're changing our K to a capital K. And I'm going to have a separate presentation that goes through all these of what's local, what's global, and what is local versus global coordinate system, and what is local versus global form. See, and note with, I'll try to do that my best in the presentation here, but I also have a separate presentation just on that, and you can make sure you look for that in the notes below. I'll give a link for that. All right, so we have our global stiffness matrix. All right, so let's do a Mathcad example to see how this all fits together. Right? So we're going to have this, and we're going to put that into what we're seeing here. So we're going to do a step-by-step process here, looking at this truss. All right, so basically this triangle, equilateral, 100 inches for one element, 100 pounds being applied horizontally here at the top. The modulus is 1 times 10 to the 6th psi. Got an area here, 0.1 inches squared. E times A, we're going to see this commonly, so we're already going to multiply that out, 100,000 pounds, and again, length of one member is 100 inches. So we're going to be finding the displacements of each node, the support reactions that are pinned in our roller joint here, and we'll also look at the stresses in each element, solve for that. All right, so let's get to it here. All right, so just following that solution path that we have for finding an element. First is the pre-processing phase. We need to determine what the nodes in our elements are. We need to declare what they are up front. So this is what we're going to do. We're going to say we've got node 1 here in the bottom left, node 2 on the right, node 3 at the top, and then element 1, 2, and 3. And again, we have to specify very carefully how these are set up. So here's a table to show you that. Element 1 is made up of node 1 and node 2. And referring back to what we talked about previously when we talked about node I and node J, for element 1, node I is 1 right here, and node J is 2. So when we look at theta, we're measuring up from the horizontal. How does node J move up from the horizontal? It doesn't in this case, so our angle is 0. I forgot to put the degree sign there. I'm going to try to fit in there real quick. And so then for element 2, node I is node 2, and node J is 3. And you can see if this member kind of started out like this, and then it worked up, and we measure the angle like this, we would get an angle of 120 degrees, because this interior angle here is 60. So the outer one here is 120. You could also do it differently. You could also have said element 2 is node I is 3, and node J is 2. And again, if you measure from horizontal, you could either measure this way and go around, or you can measure this way. All right. As long as you're consistent and you get these things right, you're okay. I would just focus on horizontal here. 2 and 3 should work out just fine. All right. Let's look at element 3. So element 3 is right here. Node I is 1. Node J is 3. So just measuring up from horizontal, and we're going to get 60 degrees. So that's where the 60 comes from. All right. So we got our nodes defined, we got our elements defined, we got our angles defined. We're in a good place. All right, so step 2, we're going to assume a solution that approximates behavior of an element. All right, so we kind of already did this. We said, okay, our equivalent stiffness is going to be our AE over L. And AE, we already defined 100,000 pounds divided by the length, 100 inches. So our K, or stiffness value, is 1,000 pounds per inch. All right, so let's do that. Let's go see what we can do that in Mathcad. All right, so here's your Mathcad file. Oh, by the way, here I'm running Mathcad Express. So I do not have a license on this, what I'm running right now. So you should be good if you just want to download the free version of Mathcad. Sorry for the ads on the side. I think with Express, oh, I can't get rid of that. All right. All right, so here we go. We got the modules, 1 times 10 to the 6th psi. We got the area 0.1 inches squared in the length at 100 inches. And by the way, if you haven't figured this out yet, I'll just show you how you can plug that in. If you, let's say M, and then M colon to find the value, say 90. And then if you want to put in the dimensions, you can just type in what those dimensions are, so 90 inches like that. And you should turn blue, indicate that it's been a dimension. So I just wanted to highlight that when you get a chance to do that on your own. All right, we've got our diagram over here to see what's going on. So scroll down here, and we've got K is our stiffness matrix that we showed from before, the development of from the forces and the stiffnesses being applied to our single element. And I'm just going to click on that and hit equals to see what those values are. And everything else is in English units on this, so let's be consistent with that. That's what the note's here for. You'll need to change the units to pound force inches. So let's do that. We're just going to backspace out the kilogram inches and just type in pound force divided by inches. Enter. Right, you can see that comes out nice, much more clean values for us there. All right, so that looks good. So let's go back to the presentation here. All right, so we're going to develop equations for our elements. So we need the stiffness value, the global stiffness matrix. So that's our here's our K value out front, multiplied by our cosines, that have been set up here. So again, this stiffness matrix that we made over here in Mathcad, to be clear, local coordinate, right here, local coordinates, local form. I'm going to go back to the presentation. This is the local coordinates, but it's in the global form, where we're using the capital K. Right? We're in the local form because we're still got an E here. All right, so let's look at that. So here's our development of our global coordinates, but local form of our stiffness matrix. All right, so for element 1, we know the angle is 0 degrees. So we plug it in 0 degrees up top, and we come up with our global coordinate form is what you see there. And we're going to do the same thing for element 2, put in 120 degrees. All right, again, these are all back from the table, back in step 1 when we define nodes and elements. Right, we get the values there. And for element 3, 60 degrees, we get the values there. Okay. So I showed the corresponding nodal displacements because this is element 2 is made up of nodes 2 and 3. And element 3 is made up of nodes 1 and 3. All right, so we're going to head and do that, see how we do this. All right, so we're going to scroll on down here. So the transformation matrix, I already put this in. So that's for a truss. Now this is, the overall transformation matrix. So we're going to go down here to element 1, and we're going to put in the angle. So you can see it's radians to start with as the default. So we want to get our angle from degrees to radians. So for element 1, it's 0 degrees, and just hit enter there. So it's 0 radians. For the transformation matrix, to make it easier on ourselves, I did this in terms of A. So A being the angle. And so the angle is defined here. So it's 0 at this point. So I'm going to type in, use the transformation matrix up above. That's a function of A. So I'll look here for A, and I'll look here for the transformation matrix. I hit equals, and I get all my 1s. Right. So I'll slide down here. And now I want the global stiffness matrix. Because again, up here is the local stiffness. Down here is the global stiffness. I'm trying to get the global coordinates. So we're going to pass through this one. We got T1. And just follow this form right here. Or from the presentation, so T1 times K, which was defined above, times T1. And now you got to make sure you get the inverse. So caret or shift 6, negative 1. And we'll hit equals on that. All right, again, watch the units there. So we want to change this, swap this out for pound force per inch. All right, that's what you should get there for stiffness for K1. Scrolling on down, expand this section. For element 2, we have the angle of 120 degrees. So plug in 120. Again, we get that to radians. Transformation matrix 2. Now A, because the way Mathcad works is whenever you redefine something that's already been defined before, this one takes over. So A now, because I've defined it as 0.02, it overrules the angle I defined above for element 1. So I'm going to put in the transformation matrix function of A. Right, so we get those values, and now I want to get the global coordinate form. So I'm going to put in T2 times my local stiffness times T2 to the inverse negative 1 equals. All right, again in kilograms per second, let's change that to pound force per inch. And we get that form. And scrolling down for element 3, we'll plug in our 60 degrees equals T as a function of A equals and K T3 times K times T3 inverse equals, and change the units to pound force inches. All right, so that's what you should have there. Let's go back to the presentation. All right, so capital K means we're in global coordinates, right? Global coordinates, but we're still in local form. Why? Because when we look at the nodes that are involved, we only have two nodes, and our whole system is actually made up of 3 nodes. So until you have all 3 nodes showing up, you're dealing with the local form. So that's why this is called the local form. And we want to go from the local form to the global form. So that's what we're going to do now. So we want to have something that looks like this, where we have all the nodes showing up and the elements of x, or elements of I and j on this one. So we basically want this 6 by 4 matrix to be created. So we're going to go from a 4 by 4 to a 6 by 4. So let's see if we can do that here. So here's our kind of our transformation matrix. So you've seen that before. So again, a lot of similar wording here, so be very careful with that. But you can see this back in the linear algebra review, how we have this and how this works on the setup. But because element 3, we're looking at element 3 here specifically, we only have nodes 1 and nodes 3. So we're not going to have anything in this row because there is no node 2 in element 3. All right, so that's why there's zeros here. We just have ones here and here because we're going to include IX and IY for the global displacement for node 1 the x direction and node 1 the y direction, and similarly with node 3. All right. If you wanted to, and it went the other direction, if we set it up so that our triangle like this, if we had 1 and 3, and we defined this was I, and this was j, then we just have to reposition and we'd say, here's j, and node 1 is j, so 1, 1, and node 3 is node I, and we use 1, 1 here. Right? This is what we actually did, so we're going to stick with this, but this is what you could do if you went the other direction, right, to make sure you loaded them properly. So make sure you get comfortable with that as you do some examples with that. All right. Kind of lost. Hopefully you can see through that. So that the angle will be different in the K matrix, all right, in the global form matrix, but local coordinate local form, the local form, local to the element. But when you get into the global form, all right, amongst the whole system, it'll be the same. All right, so we'll see that here in a bit. So let's do that. All right, so we're trying to go from, so these were global coordinates, local form. We're going to go to global coordinates, global form. All right, so we're going to put in our transformation matrix. So this is our 6 by 4 matrix we're going to put in for element 1. And probably the easiest thing to do is just put this in, insert this way. So we get a, let's say 6 by 4. So we get that. And element 1 is made up of node I. Maybe let's go, yep, so we'll see right here. So we got node I down here in the bottom left corner, and node J is node 2 over here on the right. So I is 1, J is 2. All right, so if I is 1, then we can put a 1, 0, 0, 0. And I'm just using the right arrow key to move here. 0, 1, 0, 0. All right, so that's, now we have I set up as 1. Now J is 2. So J starts in this one right here, so that's a 1. And we got 0, 0, 0, 0, 1. All right, so that's element 1. I'm going to come back here and backfill in the zeros that I missed. All right, so that's our transformation matrix. And now if we want to transform our local form stiffness matrix from up above that we just did, we're going to type in our trans 1, so the matrix we just created over here, times K sub 1. So it's our K sub 1 is our global coordinate local form stiffness matrix from above. Multiply that times trans 1, the transform of that. So I'm going to use Control Shift T to make sure I get the transformed version of that. Now if I hit equals here, again, it's kilograms per second. Let me change that over to pound for inches. All right. So you can see here, if we go up, so we got 1, 1, or 1, negative 1, negative 1, 1, up here in the upper left-hand corner. 1, negative 1, negative 1, 1. All right. So that's what we have here in the upper left-hand corner. So we have, if we go across here, this is node 1 in the x, node 1 in the y, node 2 in the x, node 2 in the y, node 3 in the x, node 3 in the y. So For element 1, we just have 1 and 2, so that's why it's just showing right there. All right, let's keep doing that for element 2. Come down here. All right, we need the same thing. Let me close this actually so we can see things a bit better here. We're going to do the same thing. We're going to do a 6 by 4. Oop, undo. Click there first. There we go. Now we go. So 6 by 4. All right, so element 2, go back to the slide here. Element 2 is made up of nodes 2 and 3. And 2 is node I, and 3 is node J. So let's start right down here. So node I is 2, so we'll go 1, 0, 0, 0, 0, 1, 0, 0. And node J, this kind of set of columns, is related with node 3. So we got 1, 0, 0, 0, 1. And backfill, and zeros. And we're going to do the same setup here. So we got trans 2 times our k sub 2. So again, our global coordinate local form of our stiffness matrix times trans 2 transformation of that matrix equals. And yeah, it goes off the page. So we can go to the different view here. So here's draft view versus page view. Page view is what basically you'd see when you print it off. So we go to draft view, it kind of extends it. And so we can delete off that pound force inches. Enter. And go back to page view, see if it's a little bit, yeah, it still shows. I like page view, it's a little bit cleaner as opposed to having draft extend on beyond that, but you can do what you like. All right, so that's element 2, we look good there. And let's go down here to element 3. So we'll expand this. Again, we'll put in our 6 by 4 matrix there. And now element 3 is made up of node 1 is node I, essentially, and node 3 is node J. So 1, I, 3, J. So I is 1, and 3 is J. So we got 1, 0, 0, 1. And the backfill. Looks good. All right. Let's transform this guy. So we get trans 3 times the global coordinate local form of the stiffness matrix times trans 3, transforming that, equals, all right, it takes me back to the giraffe version here automatically. We'll change the units. And get back to page view again, like being a little bit more clean here. All right, so then we get the different positions there. All right, so let's look what happened here. All right, we created these global matrices. All right, we created this, 1, 2, and 3. That's what we just created. So we're going to add these together to create the global coordinate, global form of the stiffness matrix. All right, so it ends up being a 6 by 6 because we have 3 nodes and there's two components at each node we need to be interested in. All right. So element 1 shows up here because it's made up of nodes 1 and 2. Element 2 shows up here because it's made up of nodes 2 and 3 in the bottom right versus the top left. And note here what I try to do too is you can see the where it overlaps, you see the colors. So blue and red gives you purple in the middle. So that's where we have some adding and subtracting going on. Now, what about element 3? Element 3 is made up of nodes 1 and node 3. So for node 1, we're going to see it here as well as here because of being involved with node 1. And for node 3, see it here and here. So again, it's basically element 3 is yellow. So where yellow overlaps blue is green, and where yellow overlaps red, we get orange. And then we get yellow in the 2 corners. All right, so that's where they all come together when you get added into this global matrix, global stiffness matrix. All right, so let's go do that. Really easy. So come down here and get our global stiffness matrix. So our kg value here is just kg sub 1 plus kg sub 2 plus kg sub 3. All right, I'm not going to hit equals on this line because it it'd be to go off the page here. So we'll just do it on this line here and update the units here. Just click right on past them. Delete these guys. Come on, get out of there. All right, pound force per inch. All right, so we can see all those values. And actually right here we can catch these values here from the local form, or sorry, global form for just element 3. And then we see that these terms are added. I can't really see them here added in here, but these terms are not added in anywhere. They're right here in those spots, and these 4 guys are in these 4 spots right here. All right, so we can see those come through. All right, so there's a global stiffness matrix. Let's go back. All right, so there's it all added together. So now we're going to apply boundary conditions, step 5 in our process here, boundary conditions and load. So we got our picture here in the upper left, so we can refer back to that. Here's the setup here. So we got the global stiffness matrix times the displacements times the loads. And boundary conditions here, we have the pin joint restricts us, so we have no displacement at node 1 in the x or y direction. So because we have no displacement in the x direction, we can knock out the whole first row and the whole first column. Now we could change this to 1 and make everything else zeros, but the easier thing, at least when we're doing this in Mathcad, is to just wipe out these rows. So we can do that. And then we can also, there's no displacement in the y direction, again, because of the pin joint. So those can go. And then no displacement in the y direction because of the roller joint. So those can go. So because these are all equal to 0, we can eliminate the first, second, and fourth rows and columns. All right, and so we can just whittle it down to just the 3 by 3 stiffness matrix, because the other ones we just ignore. We know they're 0, so we're not going to try to solve for them. We also have our load of 100 pounds, and the 100 pounds is acting in the global x direction, right? Globally in the x direction at node 3. So that's why we apply 100 pounds right here. And that's why we needed the global form. We couldn't have done this in the local form because it's not being applied in this direction. This is really all when we're saying these members are only 2 force members, we have to apply this on a global scale. We can't really apply it on a local scale. I guess we could have broke it into components and do it that way, but we'll see how that works out here. All right, so how do we do this? How do we whittle this guy down, take out these rows and columns, and get to what we want to do? Well, we use what I'm calling the boundary condition matrix. It's another transformation matrix, but we only include what we want to keep. Right? So what we want to keep is the displacement at node 2 in the x direction. We want to keep displacement at node 3 in the x and y direction. So there's a 1 here, here, and here. So it's a 6 by 3, 6 because we have 6 different coordinates between our 3 nodes. And then it's a 3 because those are only 3 displacements that are left to solve for. All right, so there's the u2x, displacement at node 3 in the x, and then displacement at node 3 in the y. So we can reduce that matrix down to this, which I'll show you here how to do in a sec. All right, and we can solve that linear system of equations and come up with these values for our displacements. All right, so let's go do that. All right, so we're going to apply boundary conditions. All right, so boundary conditions, again, it said it was a 6 by 3. So we'll get up our 6 by 3 matrix here. And we want to keep the displacement at node 2 in the x direction. So that's here. So these first 2 are for node 1. And we also want to keep node 3 in the x and the y direction. All right, and then we'll backfill with zeros. All right, so that looks good. So the reduced form of our global stiffness matrix, so the sub R here stands for reduced. The reduced form, how we get that is we're going to take the boundary condition matrix. We're going to take the transform of that times our global stiffness matrix in global form times, again, the boundary condition matrix. So instead of developing it into the global form, we're kind of hacking it back using the same process. All right, and again, fixing the dimensions, the dimensions, units. All right, so we get that form, so that looks good. Now let's look at our force matrix. So this is our 1 by 6, and so it was 0, 0, 0, 0, and it was 100. So at node 3 in the x direction and 0. And we want to cut that guy down too. And the way we do that is we're going to put in the boundary condition matrix, the transform of that, times our global force matrix equals that. All right, so we keep just the force playing node 3 in the x direction as well as the other two displacements that we're interested in. All right, so let's get down to the solution phase here. We'll expand this section here. All right, so we're looking at finding the displacements in our reduced form. So we got kg sub r, so our stiffness matrix. And to solve a linear system equation, we take the inverse of this and multiply that by, negative 1, and then arrow forward to get out of that superscript, times the global force matrix in the reduced form. And we solve for, our values in inches. Let's see what happened here. Oh, I forgot to label these up here. Make sure I add this up here. We need a label for units on their force. So I'm going to click just outside the matrix there. You see it blinking there. So call that pound force and enter. See, this updates to newtons. We'll fix that to pound force. And sliding down here, that fixed itself right up. So that's in inches. Good. All right, so making sure we got units all the way through. All right, so again, this is the reduced form, and then just to put that back into a global form where we can see the displacements of all the different coordinates or components at all the different nodes. We're going to multiply times the boundary condition matrix times the reduced displacements matrix, and we get that. So we get our 0, 0 displacements and 0 at node 1 and node 2 in the y direction, and then we get the other ones that we developed over here. All right, so that all looks good. All right, so now step 7 is we want to obtain some other information. We don't want to just have the displacements. We also want to find reaction forces, stresses. All right, so to get the reactions, as we looked at before in the direct formulation lecture or presentation, we have the reactions are equal to the global stiffness matrix times the displacements minus the forces. All right, and here's our reaction matrix. And we can perform those matrix operations and solve for the reaction forces. And just to do a sanity check, does this make sense? We got 100 pounds being applied in the x direction. We should see 100 pounds reaction force because this is the only point preventing this thing from slotting in the x direction. So we see a negative 100 there being applied at node 1. So that looks like we're on the right track there. All right, so let's do this. All right, so come down here, we're going to post-process with our reaction forces. So we got R, and that's going to be equal to our global stiffness matrix times our global displacements minus the global forces. And it equals our matrix, and updating the units. And right there. All right, so that looks good. And you're going to see this a lot as we go through this. It's not come out to just 0, but it's 10 to the minus 15 is essentially 0. So just heads up for that as you look at the results in some cases here. All right. Come back here. Let's look at our internal and normal stresses. So for each element, we have already got the global displacements, and this is going to be equal to the transformation matrix times the local displacements. So we have these, we want to get these. So to do that, we multiply both sides by the inverse of the transformation matrix to work ourselves back. So we got the global displacements multiplied by the inverse of the transformation matrix. We can find our local displacements. All right, so local displacements can be found for each element since the angles and the global displacements are known. And so once we know the global displacements, we can figure out the force. And if we know the force, we can get the stress. So if we got force divided by the area gives us stress. And because the force is equal to the change in displacements times k, we can plug that into the numerator. K we know is AE over L, and solving A is going to cancel out. So stress is basically the modulus times the change in local displacements all over L. All right. So note these signs. The signs we have for a negative sign in front of the I x component and a positive sign in front of the node J x component. It's so that we get tension. A positive value indicates tension and a negative value indicates compression. So that's why those values are as they are. All right, so element 1, local displacements. So we're going to start with plugging our global displacements and our inverse transformation matrix. And so here's our global displacement, 0.05 inches that we found at node 2 in the x direction and 0 everywhere else in our inverse transformation matrix. Solve that for the local displacements, and hey, it comes out to 0.05. Now this is because the angle here, if you remember for element 1, the angle is 0. So that's why it doesn't change between the local and the global coordinates. All right, for local forces in element 1, all right, we're going to plug in our stiffness matrix for our element times the local displacements we just found. We can figure out the local forces. And we get the local forces at x in the node I, and x in node j is -50 and 50 pounds. Looks good there. So finding the internal stress, all right, we got the local displacements, and we can substitute in for those and come up with 500 psi. It being positive, it is in tension, so the T stands for tension here. We can also do this for elements 2 and 3. All right, so for element 2, we plug in for our inverse transformation matrix and our global displacements here on the right. Solve for the local displacements. Same thing for element 3. Now we're at 60 degrees for this element, and we have the local displacements there. And solving for the local forces. Right, so substituting for the K matrix and local displacements. Again, K is the same for all of our elements at this point. So we got 100 pounds there at node 2 in the x direction, negative 100 pounds at the node 3 in the x direction. And element 3, you can solve for those forces again, negative 100 and 100 pounds. So when we plug this into our stress, we have our stiffnesses in the x direction, and that comes out to be having compressive load in node 2, or element 2, excuse me, and tension load in element 3. And that's what we expect if we had the triangle like this, and we had the load being applied this way. We'd expect tension to happen here in element 3. We'd expect compression here in element 2, and we'd expect tension in element 1, which we had. All right, so that concludes this presentation. I didn't get a chance to show you how to do the elements, finding the stresses and stuff in Mathcad, so I'll leave that as an exercise for you, and I think we'll actually end up covering that in the future presentations. So let me know your thoughts in the notes or the comments below, and hope to see you for the next one.